Hey class, Mr. Moyden here with a video on a new topic. We're taking the idea of trigonometry, which deals with right triangles, and moving beyond right triangles and extending trig to other kinds of shapes. So let's go ahead and dive in. So most of our study until now has been focused on the right triangle, right? So SOHCAHTOA, which is our primary tool for approaching right triangles, which is the one way of understanding sine, cosine, and tangent, are or it depends upon having hypotenuse, which of course is unique to a right triangle. So opposite hypotenuse, adjacent hypotenuse, and opposite adjacent only make sense when you're dealing with a right triangle. But of course, triangles come in two other varieties. Of course, we have the acute as well as the obtuse. And a category name for both of these shapes, which is sort of the opposite of a right triangle, is the oblique triangle. So both of these acutes and obtuses here are subcategories of the broader family called oblique triangles. And as such, we cannot use the traditional SOHCAHTOA trigonometry methods we have been using because, for example, there's no hypotenuse in this shape because there's no right angle, and similarly for this obtuse triangle. So the two tools we're going to be using, and they're actually applicable to both shapes. It's not as though one's for acutes, one's for obtuse. Both shapes can use these two tools. These are called the laws of sines and cosines. So we'll be learning this one in short in the video here. The law of cosines we'll see further on in class. So let's go ahead and figure out what the law of sines is, although before that we do have to establish a little bit of a standardized system for making sense of non-right triangles. So since we don't have opposite, adjacent, and hypotenuse anymore because we no longer are dealing with a right triangle, we need to establish some sort of standard way to refer to parts of shapes. So the typical way that we do this is to agree upon calling the side lengths in a triangle. So let me go ahead and label the corners here, the vertices to be precise, A and B and C. So since I can't label these things as adjacent and opposite and all this, or hypotenuse especially, the labeling system we're going to use effectively is going to be the following. Any side length is going to be labeled in the lowercase letter of the angle across from it. So for example, I have angle A right here, right? So the side length directly opposite from A, the angle, I'm going to call this length right here lowercase a. And from this angle here, B, the side length opposite from it, I'm going to call this side length lowercase b. And finally, my remaining side length is opposite from angle C, so it's going to be lowercase c. So it's just a sort of standard way to refer to sides and angles in this manner. The opposite angle and the side length have this lowercase uppercase relationship. It's just a standard way to label things. So with that in mind, let's take a look at the following generalized case. Here we have that same system here. And when we try to think about, finding relationships among the sides and angles here, we're kind of at a loss because our normal go-to, which is SOHCAHTOA, falls apart, right? We don't have a hypotenuse here, and our reference angle sort of, which one do we choose? They're all acute. There's no better choice necessarily. So rather than try to reinvent the wheel, let me see if I can turn this into a right triangle problem. In other words, if I can basically extract a right triangle from this scenario, then maybe I can use my old tricks of sine, cosine, and tangent. So what I'm going to do is I'm going to drop an altitude from the angle C. So I'm going to basically split the original oblique triangle into two right triangles. So I have a right triangle over here, well, you get the idea. I got a right triangle over here, a smaller one, and a right triangle over here, a bigger one. And I'm going to see what I can do with those two right triangles because, of course, we've been doing a lot of work with them, and it makes sense to see if our old skills can apply in this new context. So I went ahead and called this altitude h because it's the height of the triangle from this perspective. So let's focus on the first small triangle here. Even though it's not the full triangle, it is correct to say that in this small little subsection, let me try to color it if I can, just for clarity's sake. In this green triangle, the sine of angle A is opposite over hypotenuse, or h over b, right? Similarly, in this orange triangle, you can't see the h anymore, so I'll undo that. In any case, in the, I suppose, white triangle now, we have opposite of angle B as the very same h over a. So from B, the opposite is h over a. Again, just dealing in the right triangle subsection that I've created. So sine of b is h over a. So these are just two math facts that are extractable from these sort of smaller problems within the overall question. I'm going to recognize that both of these have an h in them, and that might be a useful observation, which is to say, let me solve both of these problems independently for h. So if I multiply both sides by b here, I would get b times sine of a equals h. And likewise, if I multiply both sides by a here, the a would cancel here, leaving me with a times sine of b equals h. So the reason this is useful is I now have two different representations, two different ways to express the same quantity. This business right here, let me try to highlight it. Whoops. Apologies. This business right here is a way of describing the length h. And this stuff right here is also a way to describe the very same length h. So since they're describing the same thing, by the transitive property, these two quantities are equal to each other. This stuff over here equals h, and this stuff over here equals h. So this part's kind of tricky. It's sort of unusual, it's sort of arbitrary in a sense, but one thing to keep in mind in math, especially with equations, is anytime I have two things equal to each other, I'm really free to do anything I want as long as I do it to both sides. So if I, for some reason felt like I needed to multiply both sides by 3, I could do that, and I'm just pulling 3 randomly. I can do that as long as I do it to both sides. So I can do anything I want as long as I treat both sides fairly or equally. And I'm going to choose to divide both sides by the quantity b times a. So divide both sides by ba. And the reason I want to do that is I have this pesky b here and this pesky a there. And we'll see what happens if I can sort of switch their spots. So dividing both sides by ba would give me this quantity here. Divide this side by ba, divide the right-hand side by ba. And what you'll notice is these lengths right here will cancel. And the a's will cancel, leaving me with something kind of cute. Sine of a over a equals sine of b over b. And through a very similar procedure, we won't go through it in rigorous detail, but the same basic premise can be used to show that it's also going to be equal to sine of c over c. So actually all three of these guys are the same amount. And this rule right here, this final result, this law of sines is a property that's true for all triangles, especially obliques, but really all triangles. This also works for right triangles. So this is the law of sines. We'll be using it quite a bit in class. So this video primarily is to show why it's true. Let me illustrate an example of the law of sines briefly in a numerical instance. So if you take a look here, you'll notice that I can make this triangle any type of oblique triangle I wish. And in the corner here, you'll notice they have the ratios flipped, but it's still the case that reciprocals are equal. But in any case, angle of 50 degrees, 18.3, that's this middle fraction. 80 degrees and its opposite side of 23.6, that's this first fraction. And likewise, let me adjust this for the remaining, and you'll see that all three of those quantities are equal to the same amount. And that's the law of sines. So we'll talk some more about this in class.